All right, everybody, this is section 4-6. We're going to look at the graphs of the other trigonometric functions. So we've already talked about the parent graphs for sine and cosine. Now we're going to talk about the parent graphs of the other four. So today's kind of part one is tangents and cotangents. So these first two essential questions here. What does the graph of tangent look like, and what does the graph of cotangent look like for our part one? So I want to talk first of all just about just the basic values. We're going to make a table of values again like we did for sine and cosine. There's a little bit different things that happen with tangent and cotangent because of the values. If you think of the values of tangent, it's the same as slope, remember? So we have things like 0, square root of 3 over 3, 1, square root of 3, but then at 90 degrees, tangent is undefined, right? Remember the slope of a vertical line, undefined. So the graphs of these are very different than what they are for sine and cosine. So let's go ahead and make a table of values and just get a quick sketch here so we can see what this graph is going to look like. And then I'm going to show you on Desmos a few of the things that can happen. So we're going to look at, go ahead and just make yourself an XY. I'm going to start at, we're going to do some negative values and some positives, just like we did before, but not nearly as many as what we did for sine and cosine. But we're going to start at negative pi over 2, and then we're going to do negative pi over 4, and then we're going to do 0, pi over 4, and then pi over 2. So we're going to look on either side of the y-axis and see what happens for each of those values. So let's do the 0 first because that might be easier for your calculating. So when you do tangent of 0, horizontal, that would be 0. Tangent at pi over 4 is 1. Tangent at pi over 2, undefined. Then we go in the negative direction. Negative pi over 4 would just put you in quadrant 4. So tangent is negative 1, negative 45 degrees. And then at negative pi over 2, that's the same as 270. That would also be undefined. So let's see what that looks like for our graph. So we're going to go ahead and label. There's still 4 intervals, but just the parent graph for tangent, it's easier to do those 4 intervals, 2 on either side instead of just all 4 going one direction here. So we have pi over 4, pi over 2. And we have negative pi over 4, negative pi over 2. And it looks like for our vertical scale, 1, negative 1 should be good to go. All right, so let's graph the points that we have. So we've got 0, 0. We've got pi over 4, 1. Negative pi over 4, negative 1. And then how do we show this undefined place? Well, it's a break in the action. This is not a continuous graph. It is discontinuous. And so we show that break. It's actually a vertical asymptote. It's an undefined situation. And it's the same exact thing as when we did parent graphs earlier in the year. If we think about what the definition of tangent is, tangent, the function itself, is equal to sine over cosine. If you remember your trig identities we did before. So tangent is going to be undefined wherever cosine of x is equal to 0. So where cosine is equal to 0 is at pi over 2 and negative pi over 2. Those undefined places on your graph, that leaves you with a vertical asymptote. So when we think about why this is happening, it's the same exact thing as any other parent graph. It's going to have that vertical asymptote because we can't remove those discontinuities. When cosine is 0, tangent's going to be undefined. Okay, the basic shape then of the graph, it continues to approach as we get bigger and bigger values. Like we could do square root of 3, we'd have another value. The end of the graph ends up kind of looking a little bit like x to the third, but again, it has asymptotes, so it's a little bit different. So that's the parent graph for tangent. It's going to continue to increase towards that 1 at pi over 2, and it goes down to negative infinity when it gets closer and closer to negative pi over 2. So some interesting things about the graph. This has symmetry with respect to the origin. So we have points on equal distance. So this is an odd function, so it has origin symmetry. So that's why that graph looks like that, just like our x cubed does. The period of the tangent function, how long does it take to get through one complete graph? Well, it starts at negative pi over 2 and goes to positive pi over 2. So that's a distance of, you have half of pi on one side and a half of pi on the other side. So the total period is pi. That is different than sine and cosine. So our parent graph has a different kind of period than it did for our other two trig functions. So it's shorter. It's only pi. That means our period formula for tangent is pi over b, not 2 pi over b, pi over b. The original graph is only pi long. So on that interval from 0 to pi, the place where it's undefined has vertical asymptotes at any multiple of pi over 2, remember. So that's where cosine is 0. So anywhere cosine is 0, then tangent's going to be undefined. So that means our domain isn't all real numbers. We have these asymptotes, these breaks in the action. So at all of those multiples of pi over 2, so the undefined places, this domain, it's all real numbers, but x can't be equal to pi over 2, and then any pi over 2 after that or before it. So these are pi apart, so our period is pi, so every pi before and after, we're going to have trouble. So they usually say pi times n, where n is an integer. So in other words, all the multiples of that pi over 2, but every pi before it and every pi after it. So at pi over 2, then it would be 3 pi over 2, and then again at 5 pi over 2. So all of those places we're going to have undefined. That's every place where cosine is 0. So where n is an integer. Don't usually have to write out too often what the domain is, but we know that there are breaks, right? There's undefined places. But the range, the output, arrows on both ends, that means the range is all real numbers. It extends infinitely in both directions, up and down. So I want you to see just really quick. I put this in on Desmos, and you can do this too. This is a tangent function then, and you can see how it does repeat over and over again. So it's not just that one on either side of the x-axis. This graph is continuing in both directions, and it's repeating every pi radian. So each one of these is pi long. So when we look from the difference here, this is our negative pi over 2 to pi over 2. This is one complete period. So this is one complete graph of tangent, but then it just repeats over and over again. All right, so guess what we can do with this? We can move it around, right? So all of those values, if you look up here at our equation, all of these values do the same sort of things as what they did for sine and cosine. So we need to talk a little bit, though, about the amplitude idea, this A for amplitude. So we're going to try to think about, what does amplitude measure? So amplitude, remember, is the distance from the middle of your graph to the topmost point and from the middle to the bottom. So if your graph is continuing infinitely in both directions, is there a top? Well, no, it continues infinitely high. Is there a bottom? Well, no, because it's going infinitely small. So really, there's no amplitude number we can measure. Tangent graphs do not have amplitude. However, this A value is still a vertical stretch or compression. This still vertically stretches and compresses the graph, but there's no technically amplitude number, because that's a measure of a distance from the middle to the top or the middle to the bottom. So that's kind of a unique feature about these tangent graphs. There's no amplitude. So there's no amplitude that we can measure, but the A value still does the vertical stretch and compression. So if you're asked, hey, what is the amplitude of this tangent graph? You can't measure that. That's something that doesn't exist. However, again, the A value still does what we think it should. So let's talk about that and what all these values are going to be doing here for each one of these. So the A is going to tell you the vertical stretch or compression. So just like it does for all the other graphs, that's no different. So stretch or shrink, compression, whatever word you want to use. So the bigger that value is, the bigger the stretch. Remember, if A is less than 0, then that graph is reflected over the x-axis. So we'll take a peek at that. We'll look at some of those on Desmos. Think about what the other values do. The B value talks about period. So the period of this function is pi over b. So remember, the original parent graph is smaller than what that original one would be. Phase shift, so all of these things are exactly the same as what they are for sine and cosine, is the c over b. Remember, you can just divide those two, or you can set that bx minus c equal to 0 and just solve to figure out what that phase shift is. And then our vertical shift comes from that d value. So if it's positive, that means it goes up. If it's negative, it goes down. So all of those things that we're used to seeing, that's exactly the same as what we're going to have for this tangent graph. So we'll be able to see what's going on with that. So let's take a peek, and we're not going to do a lot with these. We're not going to talk about tons of things, but I do want you to see what those different things could be. So we're going to add one example for tangent, and then we'll take a look at cotangent and do the same thing. So let's take a peek at this. I want to be able to list the information about it, and we'll take a look at what each of those numbers do. So let's make our list. So again, amplitude, if you were going to start with that, because we have for the sine and cosine graphs, you have to say there's no amplitude technically. So there's no amplitude value, but there is, and I would want you to be able to say this, there is a vertical stretch, right? That number is bigger than 1. It's that 3 value there, the A. So that's a vertical stretch by a factor of 3, and this graph is reflected over the x-axis. So we do have a reflection because it's negative, and we have a vertical stretch of a factor of 3 because the A is 3. The number still does something, right? It's still stretching that. We just can't measure an amplitude technically because there's no top and there's no bottom. All right, period. Remember, it's pi over b. So now we just have to be careful what the b value is here. B is the coefficient of the x term. Remember, there's a coefficient on the top there of a 1. So the b is actually 1 over 2. So b is a half. So this would be pi divided by a half. All right, well, if it's pi divided by a half, dividing by a half, remember that's multiplied by the reciprocal, that would be 2 pi. So think about what happened to your graph. Normally it was pi, now it's 2 pi. So we've made it twice as long, so that's a horizontal stretch. So that's what happened to the graph. Now, is there a phase shift? Well, do you see any parentheses with adding and subtracting? Nope. So there's no phase shift, so there's none, or you can say 0, whichever makes more sense to you. Is there a vertical shift? There's no adding or subtracting, so again, you can say 0 or you can say none. Doesn't happen, right? It's not any of those. All right, so here's what I would do if I'm going to graph a tangent by scratch here, or by hand. I would go ahead and set up 2 intervals to the right and 2 intervals to the left. The easiest parent graph for tangent is showing 2 on each side instead of 4 altogether. Then we can get that one complete curve. When we think about what happens for tangent when we make those graphs, at the beginning and the end of tangent, it's undefined, and then we have the 1 and the negative 1. So all of those things work the same way, and then if we have a vertical stretch, again, we know it's going to move those points. So let's think this through, what this is going to look like. So how are we going to do these labels? So if the entire period is 2 pi, that means half of that would have to be to the right of the x or the y-axis, and the other half would have to be to the left. That means there's going to be a distance of pi on either side. So that means this one would be pi, and this is going to have to be negative pi. So halfway would be pi over 2 and negative pi over 2. So we've stretched it, right? There's more on each side than what there was before. It's twice as wide. All right. Now, we can plug in values. It's really easy to do this. If you're not sure what the numbers can be, you can actually make a table of values and start substituting the numbers in to see what happens. So I'm going to try that. Let's put in 0. If you put in 0 back into this original equation, you'd be doing the tangent of 0 over 2, which is tangent of 0. Well, tangent of 0 is 0. And then you're going to multiply that by negative 3. It's still 0. Doesn't change at all. So that point, the middle of a tangent graph is the middle. That's where that point always is. All right, well, pi over 2, that was normally where that undefined place is going to be. If you plug it in, pi over 2 divided by 2, that means pi over 4. Tangent of pi over 4 is 1. So normally, this point would be up at 1 at pi over 2. That's the normal parent graph, right? We go up to 1, but then we have this vertical stretch of 3. So if I'm putting in this pi over 2, you end up taking negative 3 times the tangent of pi over 4. Remember, we divide there. So this would be 1 times negative 3. So the actual output there is a negative 3. Well, let's think about that when we graph like our sine and cosine. Normally it would go up to 1, but it's going to be 3 times as big because we times by 3. So it would normally be at positive 3. But look, we got the negative out front as well, which means it's reflected. So it's going to go down to negative 3 instead. So everything that it would have done for sine and cosine, it's going to do the same thing for tangent. So it's down at negative 3 because of the reflection. Otherwise, it would have been at positive 3. That's vertical stretch, right? Normally it was at 1. Now it's 3 times as tall, but it's reflected, so the graph's going to go down. All right, when we do pi, when we plug pi in there, that would be -3 times the tangent of pi over 2. Yeah, pi over 2 is undefined. Can't do that. That one's going to be undefined. That's where your asymptote's going to be. So if you can think about when you do your graphs for tangent, the beginning and the end are always those undefined. So opposite of pi, negative pi is going to be the same thing. Now, if you can figure out where this pi over 2, negative pi over 2 would normally be at -1 in the parent graph. Well, we're timesing it by 3, so it would have been at -3, but remember we're reflecting, so it goes up to +3. So instead of the graph increasing left to right, it actually decreases left to right, and it is vertically stretched. So if we take a peek at our Desmos here, I'm going to try to get this in there for you so you can see what that would look like. So we put in an A value of -3. Watch what happens when we do an A value of -3. Watch what happens to the graph. So it flipped and it got steeper, right? So we're looking at that one in the middle. And then we also changed our B value to a half. So watch what happens there. If I take my B value to a half, see if I can get it close. There we go. It made it wider. See, so we have that wider and reflected because it did both of those things. So everything you think it should do, it's exactly the same thing when we do that. Now, if you wanted to, you could see what it looks like when you do phase shift. It's the same situation, right? If we had a phase shift, it would be going left and right. And if we had a vertical shift, the whole graph goes up and down, which is kind of cool. You can see what that looks like as it moves up and down. So all the translations are the same. We're really not going to do as much with these graphs as we do with sine and cosine, but I do want you just to understand what the basic parent graph looks like and then be able to do a few transformations. We won't do like that big kahuna we did for the other one, which had all those different values. All right, so let's take a quick look at cotangent. We're going to do the same thing and see what that graph looks like. So do you remember how to calculate a cotangent? Well, it's the reciprocal of tangent. So if tangent was sine over cosine, cotangent then is cosine over sine. So if we think ahead, when is this going to be undefined? It's going to be undefined whenever sine of x is equal to 0, and that happens at 0 and pi and all of those places. So the easiest way to graph a cotangent, we're going to go ahead and just make a table of values again, is actually to start at 0 and go up to pi. It's just a little bit easier for where you can see the complete cycle. So we're going to do 0, pi over 4, pi over 2, and pi. So still 4 intervals, but it's a little bit easier to see that. So let's go ahead and calculate what each of these would be. So we're going to do cotangent at 0. Well, that's going to be the reciprocal of what tangent is at 0. Tangent at 0 is 0. So cotangent at 0 would be undefined. Remember, it's wherever sine of x is equal to 0, it's going to be undefined. Well, sine is equal to 0 at 0. That means there's going to be a vertical asymptote on the graph wherever that happens. All right, how about pi over 4? Well, tangent of pi over 4 is 1. So that means cotangent at pi over 4 is reciprocal of 1, which is still 1. Pi over 2, tangent of pi over 2 was undefined. So that means cotangent at pi over 2 is 0. And then we have, oops, we need 3 pi over 4 in there. Sorry, we need one more in here. So 3 pi over 4 and then pi. We'll move that down a little bit. So at 3 pi over 4, that's in quadrant 2. So tangent would be -1 there. So reciprocal would be -1. And then at pi, tangent of pi is 0. Remember, horizontal line slope. So that means cotangent would be undefined. So just like our parent graph for tangent, it starts and ends at an undefined place. We're just going to start at 0 and go to pi to do that parent graph. It's just a little bit easier to see the picture. So let's go ahead and get that in here. So we're going up by pi over 4. Parent graph here, I can go 1 to -1. So at the beginning and the end, just like tangent, it's undefined. And then at pi over 2, it's 0. At pi over 4, it's 1. And at 3 pi over 4, it's -1. So we have this graph that is decreasing as we go left to right. So again, similar to like an x cube, but reflected. This is the easiest way to get one complete graph for cotangent. And all it is just the reciprocals for tangent. So this one, it's an function that is also symmetric with respect to the origin. So it has origin symmetry as well. The period, once again, it's the same length as what tangent is. Starts at 0, goes to pi. So the period is pi. That means our formula for period is pi over b. All those numbers do the same thing. And then on that interval 0 to pi, the place where it's undefined is actually happening at x equals 0 and pi, the beginning and the end. So that means the domain for this one is broken up again. It's not continuous. It's all real numbers. And in this case, x can't be any multiple of pi. So usually we just say pi times n, where n's an integer. Any multiple of pi, 0 pi, 1 pi, 2 pi, negative pi, all of those places it would be undefined. But guess what? The range goes infinitely in both directions, all real numbers. So you can always generate these graphs if you just make a table of values, but understand that the beginning and the end are always undefined. The middle is always 0, and then there's going to be a 1, and there's going to be a -1. Those are the easiest points to graph. You can obviously do more if you want. So we're going to wrap up today just with one last example for cotangent. So if you can add this one off to the side there. We're not going to do a lot with these, but we do want to make sure that we understand what's happening for each one. So remember, again, just should say this, there's no amplitude for cotangent. Again, that a value would definitely stretch or compress, but there's no actual amplitude because there's no top to the graph and there's no bottom. I can't measure that. So if there's an a value other than 1, it's a vertical stretch or compression still, but we wouldn't say an amplitude. All right, so let's go ahead and make our list. So in this case, amplitude, you'd have to say none, but I would also say no vertical stretch or compression. And why is that? Well, look at what your a value is out front. It's a 1. So if a is 1, that means it's the regular parent graph. So there's no stretch or shrink vertically on this graph at all. All right, so let's talk about period. Formula for period is pi over b. Careful again, I wanted to do a couple of these fraction ones. Remember, the coefficient up top is a 1, so that means the b is a 1/4. So that means pi divided by a fourth multiplied by the reciprocal, 4 pi. This one's 4 times longer, so this is a horizontal stretch. All right, phase shift, no parentheses with adding or subtracting, so that would be a 0, and a vertical shift would be 0 as well. Not going to do, again, like I said, a lot with these, but you can definitely move them up and down, and you can move them left and right, just like the regular sine and cosine graphs. All right, so we're starting at 0. Our final interval to get 1 complete is 4 pi, so that would have to be 4. Middle would be 2, 1 pi, and 3 pi. So just like sine and cosine, the graphs look a lot the same. It's the labels that change. No vertical stretch or compression, so those are still going to be 1. All right, so let's think about what happens for these. The beginning and the end are undefined. So I know it's going to be undefined at the beginning of the period and at the end. The middle of the period is going to be at 0. And again, you can always just plug these numbers in and figure it out, right? We could put cotangent in there of 2 pi over 4. Just plug that angle measurement in. What's the cotangent at pi over 2? It's 0 because the tangent at pi over 2 is undefined. It's the reciprocal. You can always plug those numbers in. All right, so then at pi means it would be 1. So that first quarter is always at the 1, and then at 3 pi, it would be -1. So we get that nice cotangent shape. And again, this graph repeats infinitely in both directions. So it would continue another one over here, you'd have another one over there, infinitely many in both directions. So we're just showing the parent graph as this one or the original one. But remember, it continues in both directions. All right, so we have some similarities and differences to sine and cosine. We can still do all of the transformations, so all of those things that we talked about. No amplitude, remember, because that a value is just the vertical stretch or compression. But I want you to be comfortable and familiar with the parent graph for tangent and then the parent graph for cotangent. All right, so our day 1 assignment, everybody. Pretty short. I just want you to get the basic idea of what's happening. You can see everything on the screen. It's on page 315. So if you can give these a try, make this sketch, that would be fantastic. You can just do 1 full period. You don't need to do 2 unless you want to. That's totally fine. And then part 2 is going to be graphing secants and cosecants, so the reciprocals of sine and cosine.